Hello students, myself Professor Ankur. I welcome everyone for the GATE sum session on analog circuits. Today we are going to solve sums on some miscellaneous topic. So miscellaneous topics are basically mixed questions from any of the topics which are randomly considered. So we are starting with the first sum session on miscellaneous problems. Let's start with the session now. So let's take the first question. This question is from the GATE 2019 EC paper. And the question is, a circuit consisting of capacitors, DC voltage source and an amplifier having a voltage gain G equal to -5 is shown in the figure. The effective capacitance across the nodes A and B in microfarad rounded off to 1 decimal place is. So this is the question. If you can observe carefully, there is an amplifier with gain G. There is a voltage source by the name Vs. So there are in all 4 capacitors shown to us: 7 microfarad, 4 microfarad, 3 microfarad and 2 microfarad, and the 2 nodes are specified as A and B. So we are supposed to find the total capacitance between the 2 points A and B. So the first step is we will have to short the voltage source and the 2 microfarad capacitor, which is actually present between the output and the input node, which is going to work like a feedback capacitor. So for that we need to use the concept of Miller's theorem. So automatically we can see the voltage source will be shorted. There is a 7 microfarad, 3 microfarad, 4 microfarad and a Miller capacitor by the name CMI between the nodes A and B. So now if you can observe, the 7 microfarad and the 3 microfarad are actually in parallel. It will get added in series with the 4 microfarad and the resultant will come in parallel with the Miller capacitor. So for first part, we need to calculate the value of Miller capacitor. The gain of the network is -5. So the input Miller capacitor will be given as C into 1 minus AB, where C value is 2 microfarad. So 2 microfarad into 1 minus -5. So it will be 2 into 6. It will give us 12 microfarad. So now the capacitance can be found out as 7 microfarad parallel connection with 3 microfarad. So in parallel, the capacitors will get added, and whenever they are in series, the resultant is as good as the impact of parallel type resistance formulas. So that's the reason the value will be 10 into 4, where 10 is basically 7 micro plus 3 micro. So it is 10 micro and 4 micro in series. So it will be 10 into 4 divided by 14. And then the entire thing comes in parallel with the CMI, which is 12 micro. So it will get added. So it is 10 into 4 divided by 14 plus 12. So the final value is 14.86 and the unit is microfarad. So this is how you find the total capacitance between the node A and B. And the answer is 14.86 microfarad. Next question. This is from the GATE 2019 EC paper. Let's have a look at the question. And the question is, in the circuitry shown below, the input voltage V in is positive. The current I, voltage V, characteristics of a diode can be assumed as I is equal to I naught e raised to V by Vt under forward bias condition, where Vt is the thermal voltage and IO is the reverse saturation current. Assuming an ideal op amp, the output voltage V out of the circuitry is proportional to. So there are 4 options given: log E V in by Vt, twice of V in, e raised to V in by Vt, and V in square. Now if your observation is very sharp, actually this circuitry is a simple anti-log amplifier. So now we have an equation for the anti-log amplifier as VO is going to be equal to minus of I0 into R e raised to V in by nu times Vt. But since here the new value is given as 1, because in the expression of current it is clearly mentioned I is equal to I naught e raised to V by Vt, implies the nu is going to be 1. Ideality factor is going to be 1. So that's the reason the value of VO will become minus of I0 into R e raised to V in by Vt. So it is obvious that the output is going to be a function of exponential term V in by Vt. So it's a direct proportion relation. So now when I define the solution for this question, it's an anti-log amplifier and the answer is going to be answer C, because output VO is going to be in direct proportion with respect to e raised to V in by Vt. So this is the correct answer, option C. Next question is from the GATE 2018 EC paper. Let's have a look at the question. And the question is, in the given circuitry, assume that op-amp is ideal and the transistor has a beta of 20. The current I0 in microampere flowing through the load ZL is. So if you observe, this is basically a mixed logic question where we are having a transistor and an op-amp family merged together. So if you observe the op-amp carefully, the V plus pin of the op-amp is 2 volt. So by property of op-amp, the V plus pin will be equal to the V minus pin. The voltage of the non-inverting pin will be equal to the voltage of the inverting pin. Because the op-amp is ideal, the internal current is going to be 0. Hence we can say the non-inverting potential will be equal to inverting potential. Under that logic, if the V minus pin is now at 2 volt, automatically that pin is connected to collector of the transistor. So that's the reason you can find the collector current as potential difference upon the resistance. For the resistance of 10.5 kilo ohm, the top node is at 5 volt and the bottom node will be at 2 volt. So the current will be 5 minus 2 divided by 10.5 K, which will be 285.71 microampere. This is the value of collector current. So now we have given the value of beta. So we can find the value for collector current converted into the emitter current, because for the circuitry, the emitter current is basically the output current. So we can define IO is equal to IE as beta plus 1 by beta times IC, because the normal relation is IC is alpha times IE. So the value of alpha is defined as beta upon 1 plus beta. So you convert the relation in terms of IE then. So when we talk in terms of IE, it will be beta plus 1 by beta times IC. That will be the value of IE. That is the value of IO. So putting the value of beta as 20, you get the value of IO as 300 microampere. So the correct answer for the question, current IO in microampere flowing through the load ZL is 300, because the answer is 300 microampere. So this is the answer. Thank you.